Welcome to another edition of Final Countdown. We're talking about week number 11, day 3. And we are discussing the 2009 A-level paper. Right, let's get into discussion. Right. Figure shows a square plate XYBA has been removed. The moment of inertia about the axes perpendicular to the plates are. Now the moment you remove a particular mass, the center of gravity of the system will slightly shift up. Normally rectangular or square plate is at the center, no? Where the diagonals meet, slightly moves away. So from A larger distance, for B very close, C also larger distance. From this we can say moment of inertia about A is larger than moment of inertia about C, moment of inertia about B. This means answer number 4. This means answer number 4. Right. Moving on. When a guitar string sounds together with a tuning fork of frequency 191 Hz at room temperature, 5 beats per second were heard. 5 beats per second. When the tuning fork is heated up, so when you heat a tuning fork, what will happen? Length will increase. Length increases, frequency will drop. The beat increases. Beat frequency increases to 8 beats per second. Frequency of the note produced by the guitar string at room temperature is. So the logic is very simple. What is not changing? F1 is not changing. This can be either above or this can be either below. If I take above, frequency reduces, this will come closer, difference will reduce. So beat frequency can't increase. So this part is removed. Here it's going to be 5. But at this instant, if you reduce the frequency, what happens is, difference here, beat will increase. So your logic is very simple. F1 minus 191 is 5. F1 will be 196 Hz. 196 Hz. F1 is 196 Hz. Answer number 4. Answer number 4. Right? Question number 3. 5 cylindrical metal bars A, B, C, D, E are made from 5 different materials. All bars have same cross-sectional area but different lengths. Important thing is different. Here same. They are connected end to end. Free ends are at 326 Celsius. And the other end is 29. I'll again write it like this. Assume that the system is fully lagged except at the free end. Which of the material is made using the smallest thermal conductivity? So series connection, what can you say about the heat transfer? Heat transferred will be the same. Q dot equals Ka delta theta over delta L. The Q dot is the same. Cross-sectional area is the same. K is inversely proportional to the temperature gradient. They are asking the smallest thermal conductivity, largest temperature gradient. Largest temperature gradient will give you the smallest thermal conductivity. So here if I take 25 divided by 1. Here if I take 36 divided by 2, which is 80. Here if I take 110 divided by 3, which is 3 for 26.7. Here if you take it That's going to be 96 divided by 4, 24. Here if you take it, 50 divided by 5 is 10. Lowest temperature gradient is there. Out of all this is in E. So correct answer is E. Oh wait. Greatest temperature gradient. I'm sorry. Greatest temperature gradient is there. C. Greatest temperature gradient is there. C. So the smallest thermal conductivity is there on C. So question number 3. Answer is 3. Right. Many rock musicians wear special earplugs to protect them from hearing. An earplug decreases the level by 20. Delta beta reduction beta 1 minus beta 2. That is 10 log I1 divided by IO minus 10 log I2 over IO. Log subtraction is log division. I1 divided by I2 by 20 decibels. So here you have 2 equals log I1 over I2. I1 over I2 is equal to 10 to the power 2, which is 100. Factor is 100. So there you go. Fourth one, answer 3. Question number 5. When a person is wearing special spectacle lens, moves from room P to room Q, observes that a thin film of water is deposited on the room. So that means he is going from a low temperature room to a high temperature room. Low temperature to high temperature. Yeah. Low temp to high temperature, this will take place. Right. So low temperature, so this is wrong. This is correct. Relative humidity is higher. We can't say that. So when you are wearing spectacles, you are staying in a low room for on time, temperature θ1 is also low. When you go to a room which is higher, air around the glasses will also reduce temperature. And if it reduces more than the dew point, condensation takes place on the glass. So we can't say which humidity is higher. This we cannot conclude. So only possible answer is answer B. Answer number 2. Right. When we move from a low temperature room to a high temperature room, from a low temperature room to a high temperature room, the glass is also at low temperature. This will cause the air around the glass to reduce. Temperature. This causes the air around the glass to reduce temperature. And if this temperature reduces more than the dew point, condensation takes place. So when you move from an AC car outdoors or from an AC room to outside, same scenario. Yeah. Right. A charge Q is uniformly distributed along a very thin. So charge Q distributed means divide this into small delta Q charges. Include this part also, delta Q. So all are delta Q. Delta Q into n number of charges is your charge Q. A charge minus Q is placed at the center. Now a very small part containing delta Q is removed. The electrostatic force acting. Right. So if I take electroforce acting on minus Q. Negative, positive, attractive. Negative, positive, attractive. Negative, positive, attractive. This side also negative, positive, attractive, cancel off. Negative, positive, attractive, cancel off. This side negative, positive, attractive. Here negative, positive, cancel off. What doesn't cancel off is the one there. All other forces will cancel off except this. So the force there is 1 over 4 pi epsilon naught delta Q times capital Q divided by R square. And the resultant force is there in that direction, y direction. So here correct answer will be answer number 4. Correct answer will be answer number 4. Right there. The simple Q charge is subdivided into small delta Q charges. Small delta Q charges. All other forces will cancel each other off. All other forces will cancel each other off. Except for the force opposite to the empty space. Except for the force opposite to the empty space. Except for the force opposite to the empty space. Okay. Right. Question number 7. Figure shows an isolated system each having a point charge plus Q and a uniform charge conducting shell plus capital Q. So here what happens is inside electric field strength is 0. Right. What are the forces? Fa electrostatic force is 0. So these wrong. Now look. How will I find the force here? Take all the charges, keep it at the center like a point charge. 1 over 4 pi epsilon naught capital Q simple Q over d square. What about here? Take all the charges, keep it at the center like a point charge. 1 over 4 pi epsilon naught Q times simple Q divided by d square. So FB and FC are equal, FA is equal to 0. Correct answer is answer number 2. Correct answer is answer number 2. Right. 8 plus Q charges are placed. Now, can you remember? I hope you remember last time the work we did. So, we can enclose this. We can fully enclose it by a cube. We can fully enclose it by cubes. Just a rough sketch. So bigger cube. Now, what is the field lines passing through ABCD? The charges on ABCD will not produce a field or flux through ABC, but the charges behind. I hope you remember earlier work. Charge Q behind 24 surfaces, flux through cube, simple Q over epsilon naught. Flux through one surface, Q over 24 epsilon naught. Here they are asking how many charges are there? 4 charges. One surface, 4 charges. Simple Q 24 epsilon naught times 4. Q over 6 epsilon naught. Correct answer is answer number 3. Correct answer is answer number 3. One charge, 24 surfaces, QO epsilon. Scale. Through one surface, QO 24. One surface, 4 more charges multiplied by 4. You can simplify and get the answer. Right. 3 fixed resistors and a variable resistor simple R are connected. Variation of V0 between A and B, it's simple R. So when simple R equals 0, now 2R R, current can divide. If current can divide here, equal resistors, here E over 2. Here only this resistor is there, so therefore E. Potential difference is VB minus VA. V output E minus E over 2. That's going to be E over 2. All are E over 2. Right. Next one, when simple R equals infinity. Infinite means current doesn't pass through there. Current doesn't pass through there means voltage is 0. VB voltage is 0. No current is passing through. VA of course won't change. E over 2. Earlier we took VB minus VA. Now we are taking VA minus VB. So therefore there should be a difference. VB minus VA is equal to minus E over 2. So it can't be a straight line because resistance is inverse. Therefore, most suitable answer here, asymptote. Most suitable answer is answer number 1. Answer number 1. Right. Question number 10. Part of a conducting square loop side 2 meter is placed in the magnetic field. The magnetic field decreases. So if it's decreasing, somehow we have to wait, but increase it. Increase it. So dots, so field lines coming out are decreasing, so we must increase it. Current will travel in that direction, so here we have EMF. The EMF is A times dB over dt. Area of the loop is half base into height. Rate is equal to 0.8. 1.6 volt. So 1.6 volt there. What's the net EMF? Take Kirchhoff. Minus plus minus plus 3.6. 3.6 volt is answer number 4. 3.6 volt is answer number 4. Right now? So induced EMF. Induced EMF. Area is constant, rate of magnetic field is changing. From there we can find the induced EMF. Induced EMF, right. Question number 11. A box is placed on a horizontal surface and a force F is applied. So there is a box. Horizontal force F is applied with time. Which of the following graphs shows the possible variation? So if I am increasing the force, sometimes the force might be less than what? Limiting friction. If the force is less than limiting friction, this is a curve, so this should also be a curve. Applied force also will be less than limiting friction. If I increase further only, suddenly what? It will drop. So D is a possibility. Right. Next possibility, dynamic friction. When I apply, limiting friction is there. Applied force increases, friction force also increases. When friction force increases, what will happen? Right. Question number 11. No, still in question number 11. So what will happen? So this is correct. First part is static, then dynamic. Next is what? It continues to become static, no movement. Applied force increases, variation same. So this part completely static. B is also condition. It can't be straight line. So here B and D correct. B and D correct. Question number 12. Question number 12. An oil drop falling through still air reaches terminal velocity V. V proportional to R square. Forms n number of droplets. 4 over 3 pi r cube equals n number of times 4 over 3 pi simple r cube. Capital R cube n simple r cube. 1/3 simple r. New terminal velocity n 1/3 simple r square. Terminal velocity n 2/3 simple r square. Okay. So here we are applying for the new radius. No? New radius means simple r. What is simple r? R divided by n 1/3 square. New terminal velocity n to the power minus 2/3 r squared equation 2. Divide the second equation by the first. Terminal velocity of V minus 2/3 r squared. Terminal velocity n minus 2/3 V. Which means this answer is correct. Answer number 2. 12th one, answer 2. Right. Question number 13. Read the question carefully. Water in a tank is uniformly bubbled. Now, density of the mixture with bubbles is different to water. With each volume V0 is shown. A sphere of mass m and volume V floats in water as shown in the attachment. Of a certain number of air bubbles on its surface. If dW is the density of water and minimum number of air bubbles is to be added to attach to the sphere to keep it floating is. So total weight is there. Upthrust acting is V, density of water dWg, plus n number of small air bubbles are there. N number of small air bubbles are there means what will happen? The weight is which is negligible, but n number of small bubbles. V0 is the volume. N V0. Upthrust density of water into G. Actually, this should be density of the mixture, but we will take density of water. From here, we can simplify. G cancel off. M minus VW over V0 dW is equal to N. Now, this is for it to be equal. This is for it to be balanced. Minimum number. So, if the number is larger than this, guaranteed it will float. Guaranteed it will float. So, M minus VdW over V0 dW. Correct answer is answer number 2. Correct answer is answer number 2. Right now? So this sphere has air bubbles around it. Is air bubbles also given upthrust? So larger the number of bubbles, greater than the minimum, just about to sink. Just about to sink. Greater the bubbles, more upthrust is given, it won't sink. And also remember dW here. dW here is actually density of the mixture, not density of water. Density of mixture is slightly lesser than density of water. So density of water is less means number of bubbles should be more. Density of the water mixture is less means number of bubbles should be more. Right. A satellite S is moving with constant speed. Satellite is emitting radio source. The frequency when the slit moves from A to B is best represented. Observer is at P. Right. That's towards. Source is coming towards. Source is coming towards means frequency is large. Here source is going less, frequency is less. Somewhere in between, source frequency, actual frequency are the same. Correct answer is answer number 4. Correct answer is answer number 4. Right. Figure shows the curves ABCD corresponding to the magnetic image distance for 3 types of mirrors. Which curve corresponds to which mirror? Right. A. B. Plane mirror. So B is guaranteed plane mirror. None of these. Why? Object distance, image distance. No. Right. A and C only I must discuss whether it's going to be real or not. So we look at this convex mirror. Convex mirror. Image will seem like to form. So it's going to be smaller. And concave lenses, image distance is going to be large. Correct answer is answer number 2. Correct answer is answer number 2. Right. 2 strings P and Q, and P is under greater tension than Q. Figure shows the standing wave pattern. Frequency is N over 2L square root T over M. Frequency same, length same, mass per length same. When I increase the tension, what happens? Harmonic number reduces. Harmonic number reduces. Here harmonic number has increased. Harmonic number should reduce. P is under greater tension. Tension at P is greater than tension at Q. Harmonic number at P will be smaller than harmonic number of Q. This is correct. This is correct. A and C correct. Answer number 3. A and C correct. Answer number 3. Figure shows a closed PV diagram. PV diagram. Internal energy in the part C to A delta U C to A minus 160 joules. The heat transferred to the gas along AB is 200. Heat input is positive. And 40 joules along BC. Delta Q BC plus 40 joules. Work done along AB is, start with the easy one, delta Q BC, delta U BC, delta W BC. Heat transferred BC 40. Delta U BC we don't know, work done is going to be 0. Delta U BC is plus 40 joules. These are loop. These are cycle. Delta U AB CA is delta U AB, delta U BC, delta U CA. Delta U AB we don't know. Delta U BC 40. Delta U CA minus 160. Starting, finishing same. Internal energy of the cycle is 0. So 120 here. Delta U AB is 120 joules. Now if delta U AB is 120 joules, we can easily answer now. Delta Q AB equals delta U AB plus delta W AB. Delta Q AB plus 200. Delta U AB plus 120. Work done across AB is plus 80 joules. Plus 80 joules. Answer number 1. Answer number 1. Right. So what do you learn from this? In a cyclic process, internal energy change is 0. But for each process separately you can apply first law. Right? Okay. Moving on. 4 long parallel straight wires run normal to the plane of the paper through the vertices of the square. If currents of equal magnitude are set up along the wires in the direction in and out, and if the wires are free to move, the arrows in which direction the wires will move. They are asking you to find the resultant forces. How is it represented? So we'll mark the forces, no? Easy, no? Like attract, unlike repel. Unlike repel. Like attract, unlike repel, unlike repel. Like repel. Like repel. Unlike attract. Or like attract. Here. Unlike repel. Unlike repel. Like attract. So here resultant down, here resultant down. Sorry, here resultant up. Here resultant down. Here resultant up. Correct answer is answer number 1. Moving on. A and B are 2 iron columns with same exact length. A has a square side of side A. B has a circular cross section of diameter A. They are bothly fixed. A non-uniform concrete beam is placed over them. If the lower side of the concrete beam remains horizontal, the distance x to the center of gravity of the beam from them are. Right. So here there will be reactions. Here there will be reactions acting. Equal opposite. Right. F1, F2. F1, F2. Right. Iron columns made from the same material. So we'll take like this. Young's modulus is stress A square over strain. Strain should be the same. Initial lengths are same and they are horizontal. Strain should be the same. So F1 is equal to Young's modulus strain A square. Second situation, Young's modulus F2 over pi. Diameter is A, so A square divided by 4. Strain is same. Simplify this. F2 is equal to Young's modulus pi A squared over 4 strain. Now what you do? We can take moments about the center of gravity. Clockwise moments equal anti-clockwise. Clockwise moments is F1. F1 into x. Anti-clockwise moment is F2 times L minus x. F1 is Young's modulus strain A squared x. F2 is equal to Young's modulus pi A squared over 4 strain L minus x. Young's strain A squared. Young's strain A squared. Simplify this. Your job is to find x. 4x equal pi L minus pi x. 4x plus pi x pi L. 4 plus pi pi L. Pi L 4 plus pi. Pi L 4 plus pi. Correct answer is answer number 5. Right. One end of a thin elastic string attached to a small mass m and is rotated around a vertical axis. Velocity of A is given. Perpendicular string. The angular velocity of the rod object around the axis when it hits the pillar. When it hits the pillar. So what will happen? This will turn, collide straight, directed towards the center. If it rotates and collides directed straight towards the center, there is no rotation. There is no tangential velocity, so no angular velocity there. So it will turn and knock, directed towards the center. If it's going towards the center, there is no angular velocity. Right. Structured essay. Electricity structured essay. Have a look. You are asked to use a potentiometer to measure the internal resistance of a voltmeter. Its known value is to be in the order of 1000 ohms. A full-scale deflection of the voltmeter is How much? 1.5 volts. 1.5 volts. The experimental arrangement that is given below is shown. R1 is a suitable fixed resistor and R3 represents the resistance of a resistor box. Right. Now what? What is the importance of having a circuit inside the broken lines marked as Z? What is this? It's a protection circuit. Protects the galvanometer from large currents. Right there. It protects the galvanometer from large currents. Protects the galvanometer from large currents. Okay. Show how you would connect the voltmeter V to the circuit PQRS properly by labeling the polarities of the terminals plus minus. So this is not difficult. Positive terminal is connected to the positive side. Negative terminal to the negative side. That's all. No, not much of a difference. When the circuit is connected, if you observe that the voltmeter reading tends to exceed its full scale deflection, how would you rectify this? Now, the voltage across this is exceeding its full scale deflection. So what are you going to do? You must make sure what? The current passing through this will reduce. Current reduces, potential difference across voltmeter will reduce. Right there. We must make sure that the current in the secondary circuit will reduce. The current in the secondary circuit will reduce. Therefore, we must increase the resistance R3. Therefore, we must increase the resistance R3. Right. So, basic work. Write down the test that you would perform to check if all components of the experiment are arranged properly. So, what's the steps? Step number 1, I'll quickly tell. Place the galvanometer balance key at ends A and B and check if the deflections are in the opposite direction. Check if the deflections are in the opposite direction. Right there. Okay. Place the balance key at ends A and B and check if the deflections are in the opposite direction. And check if the deflections are in the opposite direction. Then move the balance key gently along the balance wire. Move the balance key gently along the balance wire. If the balance lengths of the potentiometer wire when switch T is connected to C and D are L2, are L1 and L2. L1 and L2. Derive an expression relating this. So I think we can do it on top itself, near the picture. So near the picture, if you say here, in this circuit we will say I1, R1, current goes this way, primary circuit, equals voltage across AC. I1 R1 is current into resistor, rho L1 over A. Next one. I1 R2, I2 rho over A, L2. Divide 1 by 2. R1 over R2 is equal to L1 over L2. R1 over R2 is equal to L1 over L2. But be careful. Here, if you look at the view here, I am connecting it here. So R1 plus R2 both will come. So here be careful a bit. Here we are finding the total balance length there. I1 R1 plus R2. Right. Now you divide second equation by the first. I1 R1 plus R2 divided by I1 R1. L2 divided by L1. R1 plus R2 divided by R1 is L2 divided by L1. There you go. L2 divided by L1. Right. So I found the relationship there. Rearrange the expression to plot a graph of L2 versus L1. L2 versus L1. Look at the board. R1 plus R2 divided by R1 is L2 divided by L1. So L2 versus L2 y-axis. 1 plus R2 over R1. L1 L2. Graph is of the form y is equal to mx. Right. How would you obtain a set of measurements for L1 and L2? What do you do? Change resistor R3 for R1 and R1 plus R2. Obtain different lengths. Obtain different lengths. Obtain different lengths. Okay. Right. A student has suggested another method to find the internal resistance of the voltmeter. According to his method, PQRS section in the circuit above is to be isolated and the value R to be adjusted until the reading of the voltmeter becomes 1 volt. So that means, look at the circuit below. PQRS is isolated separately. We adjust the voltage until the voltage becomes how much? 1 volt. 1 volt. That means R1 plus R3 together will have the remaining 1 volt. R1 plus R3 together will have the remaining voltage. So what can you say? Right. A student has suggested another method to find the internal side wall. If you adopt this method, write down the expression, it will give the interest of the voltmeter. So I can say R1 plus R3 times current I1 equals I1 times R2. Internal resistance is R1 plus R3. Right now, if you want to look at it, look at the circuit. Supply voltage 2 volt. Here 1 volt means remaining 1 volt across this. So I1 times R1 R3 equals I1 times R2. Okay. Give reasons as to why this method is not accurate as the potentiometer method. What are the failure points of this method? Now what's happening? You have to change this resistance until the voltage here is 1 volt. That means you are increasing the current. When you increase the current, battery 2 volt will quickly discharge. Right there. The battery in the secondary circuit might discharge. Battery in the secondary circuit might discharge. What's the next one? So here you're adjusting for 1 volt. Here you're adjusting for 1 volt. Right. What's the next one? Maybe the next main thing is you may not be able to change R3 to get 1 volt here. Like this. By changing R3, we might not be able to achieve 1 volt across the voltmeter. By changing R3, we might not be able to achieve 1 volt across the voltmeter. Across the voltmeter. Right. Essay question. Look at the board. So that the current I2 over I is given by this relationship. So what we'll do is basic work. No? I1 is here. I1 is here. I2 is there. Look at this. So if I redraw this, R0 plus R2, current is going I2, R1 here, current is I1, ratio between I2 and I. So what is I2 current? Current divided. Resistor R1 into total current divided by addition. R1 plus R2 plus R0. I2 over I is R1 divided by R1 plus R2 plus R0. There you go. So I am applying current divider. Current divider. Figure 2 shows a circuit of multi-range ammeter to measure 0 to 0.01, 0 to 0.1 with full scale deflection 100 microamperes and internal resistance 1000 ohm. So here 1000 ohm. Full scale deflection 100 microamperes. Right. P and Q represent the terminals of a multi-range ammeter, and microammeter is calibrated to read currents in both ranges. The necessary range can be selected by connecting P either to Y or Z. Okay. Think carefully and answer. Now, you need a larger resistance, and here if you connect it to Z, it will go across R1 and R2. If you connect across Y, current will go and divide across these two. Right. What are the ranges? 0.001 and 0.1 ampere using microampere. So microamperes means how much? Yeah, 10,000 amperes. 10,000 microamperes. Right. Now how will you solve this? Right. So here you have 1, 2, 3, 4, 5, 6, 10,000 microamperes. 1, 2, 3, 4, 5, 6 here. 10,000 microamperes. Next one is how much? 0.1 amperes. How many microamperes? 100,000 microamperes. Right. One is 10,000 amperes, the other is 100,000 microamperes. Okay. So what are they asking you? Question. If you want to measure currents in the 0.001 ammeter range, which terminal Z or T will you use? Explain your answer. So 10,000 microamperes. 10,000 microamperes can't go, no. Only 100 microamperes can go. 100 microamperes means remaining 9,900 across this. Clear? And the voltage here and here should be same. Lesser resistance, more current. Lesser resistance, more current. Here more current. So here these two multiplied, there will be a voltage. These two multiplied, there will be a voltage. Right. So what terminal will you select? What terminal? So if a larger current comes, we need a larger resistor. So here, larger the current, smaller the resistances, shunt resistor. So larger the current, smaller the shunt. So here your answer will be, if you want 0.01, smaller the current, larger the resistance. So it will be Z. Z, no? It will be Z, yes. Right there. Smaller the current, greater the shunt resistance. Smaller the current, greater the shunt resistance. Calculate suitable values for R1, R2. Enable you to use the multi-range ammeter. I think I'll use this space here itself. So here, if you look at it, I'll draw both the basic circuits. Easy to calculate. So if you connect it to Z here, current will divide here and there. So what we'll have is 1000 ohm microammeter. Here you have resistors R2, R1. Current is I. Current will divide here I1, divide here I2. Right. This major current is 10,000 microamperes. Full scale deflection 100 microamperes. Remaining current here 9900 microamperes. Okay. Now carefully solve this. Now what will you get? So here you can easily say 100 into 1000, 9900 into R1 plus R2. 20 cancel off. R1 plus R2 is 1000 divided by 99. Right. Next situation will be connecting it to Y. Connecting it to Y. When I connect it into Y, R0 is here, microammeter. Here in this corner, R1 also take it there, easier. Sorry, R2. R2. R1 is here. Current is 100,000 microampere. 100 microampere here. Remaining 99,900 microampere through this. There you go. Parallel circuit, 100 times R2 plus R0. R0 means 1000. 99,900 into R1. Micro cancel off, 20 cancel off. Here R2 plus 1000 equals 999 R1. Simplify. 1000 is 999 R1 minus R2. Equation number 2. So you have two equations. Now simultaneously solve. First one multiplied by 999. Problem solved. Oh, no, sorry. Or you can just add it. Easier. Easier add it. Equation 1 plus equation 2. Here 1000 R1. R2 minus R2 cancel off. 1000 plus 1000 divided by 99. All the thousands cancel off. R1 equals 1 plus 1 over 99. 100 divided by 99 ohm. R1 is 100 divided by 99 ohm. Okay. Then I can find R2. Substitute to equation 1. 100 divided by 99 R2. 1000 divided by 99. R2 is 900 divided by 99 ohm. They are asking you to find to the nearest integer, whole value. If I find for the whole value, 900 divided by 99. 900 divided by 99 is 9 ohm. Thousand divided by 99 will be 1 ohm. So 1 ohm, 9 ohm. Huh? 1 ohm, 9 ohm. Okay. Right. Write down separate expression. for internal resistance, when it's set to measure, write down separate. We have done this. This is done. We have done this. Show by drawing a circuit diagram how you would extend this circuit to figure another range zero to 1 ampere. 0 to 1 ampere. Clearly identifying the terminal. So here R0, microammeter. Here R3, R2, R1. There you go. So, what are your ranges? 0 to 0.01 ampere, 0 to 0.1 ampere, 0 to 1 ampere, 0 to 1 ampere. Yeah. So, we will rewrite this. Look at this carefully. 0.01 ampere range. Adding 3 resistors separately, we don't know. R3 dash, R2 dash, R1 dash. We calculate again. 0 to 0.1 ampere, 0 to 1 ampere. Clear? So these are your terminals, maybe X, Y and Z. Z terminal, Y terminal, X terminal. Okay. So larger the current coming, to make the current small here, in the top there should be more resistor. Clear? Smaller the current coming, so here the current is large, larger resistor, balance the voltage. Right. Essay number 2. So electricity essay was done based on ammeter voltmeter. An electric kettle as shown in the figure contains 0.8 kilograms of water. A person switches on this kettle and left the water into boil. However, has forgotten to switch off the kettle in time. And when he switches it off, only 50% of the water was found to be remaining at 100 degrees Celsius. The heater in the kettle is rated 225 watt, 2025 watt. And during the heating process, 80% of the heat goes into heating water. 20% is lost. Right. Calculate the amount of heat that is produced by the heater before the kettle is switched off. Right. Before the kettle is switched off. Okay. Right. So vaporization also takes place. Vaporization also takes place. Don't forget, when you write the equation, consider the vaporization also. So heat given equals heat absorbed. So 2025 into time into 80%, absorbed by water 0.8, specific heat capacity, I think at the end they would have given just 4200, no? 4200, right. 4200, heating water from room temperature, heating water from room temperature, so they have to give the room temperature. 20 degrees Celsius. So 100 degrees Celsius minus 20 degrees Celsius, 50% vaporizer, zero point 0.4, 2.25, 10 to the power 6. The amount of heat given is here. If you simplify the relationship, heat given 1169 joules. That's 1169 kilojoules. Right. How long will the kettle be in the on position? 2025 times time times 80%. That is 1169 kilojoules time 1169 10 to the power 3 multiplied by 100 divided by 2025 into 80. Time in seconds you can find. Time in seconds. But give me a second, what are they asking you here? Have heat that is produced by the heat. Oh. Heat given to water. Heat given to water is so much. Heat produced by the heater. So here you need to calculate that. If you simplify it, this is the relationship that you will get. So let me calculate that. Heat produced by the heater. 0.8, 4200 into 80 plus 0.4, 2.25, 10 to the power 6. That is heat given to water. 1168 800 joules. Heat produced by heater. Heat produced by heater multiply by 100 divided by 80. Thousand 461 joules. 1461 joules. Right. How long the kettle would have been in the on position? Answer it to the nearest minute. So here Now we can simplify this. Heat produced, earlier we have found 1461, right? Time taken divided by 225, 721.5 seconds, around 12 minutes, around 12 minutes, right? Next one. At what rate boiling of water would have evaporated? Minutes. Give your answer in kilogram per second. At what rate boiling water would have evaporated? Power is given. So time taken for vaporization 2025 into time, 80% of it is given. 0.4 has vaporized. 2.25 10 to the power 6. 2.25 10 to the power 6. 0.4 2.25 10 to the power 6. 1000 divided by 80 2025. That will give you 555.6 seconds. The rate of vaporization. How much of mass has gone? 0.4 kilograms. 555.6 rate. (7.2 10 to the power minus 4 kilogram per second). 7.2 10 to the power minus 4 kilogram per second. Right. Done. Assuming that water vapor in the kettle behaves like an ideal gas, write down an expression for the density. PV equals nRT. PV equals mRT over molar mass. P equals M over V RT over molar mass. P equal rho RT over molar mass. What are they asking for density rho? PM over RT. PM over RT. Right. If S of the kettle has cross-sectional area given, using the result in Roman 3, mass flow rate, calculate the speed in which the water vapor would have escaped. Mass flow rate is AB, density of vapor, or water vapor, sorry. Density of vapor. Here 7.2 10 to the power minus 4 cross-sectional area. 3.73 10 to the power minus 4. 3.73 10 to the power minus 4. Velocity we don't know. Pressure PMRT, pressure 10 to the power 5. Molar mass 0.018 PMRT. R 8.3. Temperature where boiling takes place 100. So 373. 373. Okay. So when you simplify this, you can find the velocity. 7.2 10 to the power only minus 4. 7.2 divided by 3.73 multiplied by 8.3 times 373 divided by 0.018 Divide by 10 to the power 5. Velocity is 3.32 meters per second. Speed in which the steam is going out. Right. Once the water in the kettle has reached the temperature 95, 200 cubic centimeters of water is poured into a glass cup. Don't forget, kettle has 0.8. 200 cubic centimeters is poured to a glass cup at 95 degrees Celsius, which initially is at 25 degrees Celsius. Mass of the cup is given. Calculate the maximum temperature attained by the cup of water. Assume that there is no heat loss to the surroundings. Specific heat capacity is given. Heat given equal heat absorbed. Heat is given by water. Mass of water 200 cubic centimeter, convert to cubic meter. Density of water is how much? 1000. Specific heat capacity 4200. 95 minus theta. Who is absorbing it? 250 grams of the cup. Specific heat capacity 840. Cup is initially at 25 degrees Celsius. Theta minus 25. Calculate the temperature. So 200, 10 to the power minus 6, 10 to the power 3, 4200. 840, 840 cancel off, 4 will come. 4. 4 times 950 plus 25 divided by 5. 81 degrees Celsius. 81 degrees Celsius. Okay, now? Clear? Right. So I thought I'll explain this electricity question one more time for you. Again, have a look. So what is happening here is, these are multi-ammeter. Multi-ammeter ranges are given 0.001, 0.1. So you have a smaller current, bigger current. The smaller current coming in, 100 microamperes are going. To make sure this current here is also smaller, resistance will be large. So when the current range is large, resistance is small. Current range is small, resistance is large. So current range is small, shunt resistance is large. Current is small, current is large, resistance is small. So when I'm going to read 0.01, I want more resistors, so Z I have select. When the current is larger, I have lesser resistance in the shunt. There you go. Right. So here they are given you selection. I select Z for the range 0.01 amperes or 10,000 microamperes. So voltage parallel are equal, equated, get one equation. We have one equation. Then current range becomes small, resistance becomes, current is large, resistance becomes small. Parallel, get another equation. Simultaneously solve, you can get R1 and R2. Now they are telling you, right, we've done this. We want another current. Current increases, resistance becomes even small. The smaller resistance here is a new resistors, of course. So here X will give you 0 to 1 amp. Larger current, smaller resistance. Remember like that. Larger current range, smaller resistance. Smaller current means larger resistance. So there you go how the multi-ammeter works. Multi-ammeter works. Right? Okay. So we have basic analysis of what we have done so far. So 2002, 2009 A-level paper completely done and finished. Right? What else have we done? So in terms of MCQ, 2000, 11 weeks means 11 papers, 2000, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 papers done. And the fifth week we discussed the electricity. Yes. 10 papers into 60 MCQs, 600 MCQs done. 600 MCQs done. 2008, 2009 paper we have done. 2008, 2009 paper we have done. All 4 structured essays. So there we have 2 years, we have done 8. Essays we have done mechanics, waves, fields, properties of matter, electricity, thermal. 6 essays. Like that 12 essays. From 2000 to 2007 we have done 2000, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, which is 8 papers. 8 papers, 60 MCQs each, 480 MCQs. Think about the structure. 2 structured each we have done. 8 papers, 2 structured each, 16. Essays, 2 essays each we have done. 2 essays each. So from each of these papers, so we have completed a large range. There, 16. You can see how much we just completed here. 20 essay structure, here 32, and MCQ 600. So the amount of work done there is also huge. So make sure you continue. Check and see. The more you do this, the more you become experienced in solving questions. So see you all next week, week number 12. These are halfway mark. Halfway mark. Because after next week, there will be 12 more weeks. 1 week before your exam, the final countdown will be finished. So next week, it will be 2010 A-level paper. 2010 A-level paper. Right. So see you all next week with the 2010 A-level paper. Stay safe. Keep working.